Welcome to this explainer. Today we're diving into the incredibly fascinating and honestly rigorous detective work required to build a virtual Earth. We're going to be looking at an amazing piece of research based on Arnold Sullivan's May 2026 Milestone report. Now, when most people think of climate science, they usually picture looking at the sky, maybe analyzing ice cores or measuring ocean temperatures. But there's this whole other frontier to the field, the deep, incredibly complex world of computational climate modeling. We rely on these massive simulations to predict our global future. But what happens when the simulation itself develops a glitch? Well, let's find out. To really appreciate what scientists like Sullivan are actually up against, think about this analogy for a second. Modeling the global climate is essentially humanity's attempt to capture a vast, infinitely complex ocean of dynamic Earth systems and somehow squeeze it all into a tiny cup of human understanding and mathematics. You're literally trying to translate the chaos of wind, water, heat, and gravity into millions of lines of code. It's a totally audacious goal, and it requires a level of precision that is frankly mind-boggling. Because when things go wrong in that code, tracking down the culprit is exactly like finding a needle in a digital haystack. So, here is our roadmap for today. First, we'll meet the simulator. Second, we'll analyze the 2-year glitch. Third, we'll investigate the heat budget. Fourth, isolate the physical drivers. Fifth, pinpoint the May-June disconnect. And finally, we'll map out the next steps. Okay, let's jump straight into Section 1. Meet the climate simulator, the virtual Earth. To get our bearings here, we really have to talk about ENSO, the El Niño Southern Oscillation. This is the massive climate engine located in the Pacific Ocean that basically dictates weather extremes globally. If you've ever experienced intense droughts or severe flooding, particularly in places like Australia, ENSO is largely the thing pulling the strings behind the scenes. And because it's so critical, any climate model worth its salt has to be evaluated against incredibly strict diagnostic baselines, like the Cleavar 2020 metrics. You just have to get ENSO right or your whole virtual Earth falls apart. And the tool built to tackle that immense challenge is ACCESS CM2. This isn't just some basic program, right? It's the culmination of years of development, moving from simpler physical models all the way to highly advanced coupled Earth system models. And coupled just means it dynamically links the atmosphere, the ocean, the land, and the ice, letting them all interact, just like they do in reality. And honestly, initially, CM2 was a massive success. It successfully improved 5 basic ENSO metrics right out of the gate, including its spatial pattern, event duration, and seasonality. But then we hit a snag. Section 2, the 2-year glitch, anomaly detected. So what's the specific crime we're investigating? It's actually fascinating. Even though CM2 got a lot of things right, it completely lost its skill in replicating the natural ENSO life cycle. In the real world, the El Niño cycle operates on this somewhat unpredictable 3 to 7 year rhythm. But the CM2 model, it got caught in a fast-forward loop. It was suddenly pumping out a rigid, highly regular 2 to 2.5 year cycle. It was treating a deeply complex, chaotic climate system like a perfectly ticking metronome, which of course suppresses natural decadal variability. It was too perfect, it was too fast, and it was entirely unnatural. So Arnold Sullivan's main research objective was to hunt down exactly why this was happening. And previous diagnostics had actually given them a solid clue. There was a specific breakdown in the seasonal air-sea coupling, a really vital interaction called the Bjerknes feedback loop, which is essentially how the ocean temperature and the atmospheric winds talk to each other and reinforce one another, was mysteriously decoupling. And it was happening specifically during the months of May and June. The communication between the virtual ocean and the virtual sky was literally just dropping out. Which brings us to Section 3, investigating the heat budget, gathering evidence. To figure out where the coupled model was going so wrong, the researchers needed a control to compare it to. So they compared the OM2 model, which is an ocean-only model that isolated ocean physics to track heat, with the fully coupled CM2 model that we know is glitching. By looking exclusively at the upper 50 meters of the ocean, the team set out to ensure they could successfully balance or close the offline heat budget in both models. Because, you can't find a missing dollar if you don't even know how to balance the ledger in the first place. And guess what? They did it. Through some painstaking mathematical integration, they confirmed they could close the online heat budget. I know that the data can look like a chaotic heartbeat to most of us, but to a climate scientist, this is absolute perfection. The lines tracking the heat perfectly overlap, proving their accounting method actually works. So now, they finally had a rock-solid baseline to start hunting the exact variable causing the glitch. All right, Section 4. isolating the physical drivers, interrogating the suspects. Now for the fun part. To find out which physical driver was causing the loop, they use this brilliant interrogation method called leave one out correlation. Think of it kind of like taking pieces out of a car engine, one by one, while it's still running, just to see which part causes the engine to stall. They would calculate the full heat budget, systematically subtract one physical variable at a time, say the horizontal movement of water, which is known as advection, and then correlate that new result with the true temperature change. If the correlation drops significantly, boom, you know you've just removed a dominant driver of the system. The logic applied here is just so smart. You take your full heat budget, subtract your suspect term, and run the correlation. If the correlation remains high, say around 0.99, it basically means that specific term was just noise. The system works totally fine without it. But if the correlation plummets into the red zone, well below 0.50, alarm bells ring. You have found a term that is absolutely essential to the temperature change. And the interrogation results were super striking. The data revealed that in the CM2 model, an overly estimated surface heating was being balanced heavily by intense ocean mixing. Specifically, when they removed vertical diffusion, which is the mixing of water layers up and down, the correlation dropped massively to 0.316. That marked it as the absolute dominant driver of the temperature tendency. This was closely followed by surface heat flux dropping the correlation to 0.433, and then advection dropping it to a moderate 0.788. We finally had our suspects ranked. Let's move to Section 5, the May-June disconnect, catching the glitch. When Sullivan's team looked at the seasonal variances, the smoking gun finally appeared. The data proved that advection was noticeably weaker in both the Niño 3 and 4 regions compared to the baseline. But much more importantly, the coupled model was suffering from a massive seasonal shift. The variance magnitudes for both surface heat flux and advection were entirely shifted by one full season compared to the ocean-only model. The timing of the virtual Earth was literally out of sync with reality. A glaring anomaly appears specifically in the latent heat data. During that critical May and June window, the net heat flux in the ocean-only OM2 model comfortably exceeds the coupled CM2 model. And why is that? Because the CM2's latent heat extends far, far too far west across the Pacific Basin. This completely distorts the delicate air-sea feedback. The ocean is releasing heat in the wrong place at the exact wrong time, confusing the atmosphere, breaking that Bjerknes feedback loop we talked about, and ultimately forcing the simulation into that artificial 2-year hyperactive cycle. They finally caught the glitch. Section 6. Mapping the next steps, closing the case. So, having isolated the glitch to this highly specific spatial and seasonal footprint, what happens next? Well, you document it, and you fix it. Arnold Sullivan's timeline maps a rigorous path forward for this specific project. It pushes from the deep oceanic heat budget analysis that began in mid-2026, advancing through complex shortwave and longwave radiation analysis in early 2027. All of this intense forensic climatology builds towards a final manuscript and thesis submission by September 2027. It's just a structured, relentless pursuit of accuracy. And it really leaves us pondering this incredibly profound question. We just saw how a single seasonal heat shift, a miscalculation of latent heat moving slightly too far west for just 2 months of the year, can entirely alter the simulated 7-year rhythm of our planet's biggest climate engine. Climate science isn't just about gazing into a crystal ball to predict the future. It's a relentless, line-by-line debugging of reality. It's about perfecting our tiny cup of human understanding to ensure that when we ask these models what the Earth will look like in 50 years, we are truly, undeniably prepared for the answer. Thanks for joining me on this explainer, and keep questioning the data.